everybody. Welcome back to our last day of our CILAMCE PANACM. We're going to have right now our next plenary speaker, and will be shared by Professor Sandra Malta. Sandra, please.
Hello, Álvaro. Nice to meet you. Hello, everyone. I'm Sandra Malta from LNCC, and today I'm here to present Professor João Azevedo. Thank you, Álvaro. Hi, João. Nice to see you. Hello. Welcome. Are you here?
Yes.
Yes. Okay, João. I will say some words about you. Good afternoon, everyone. In this last but not least conference, it's a pleasure for me to be here presenting João Luiz Azevedo, my friend João, a capixaba like me. Azevedo has graduated in aeronautical engineering at Instituto Tecnológico de Aeronáutica, ITA, in 1981, and he holds MS and PhD degrees in aeronautics and astronautics engineering from Stanford University. He's a senior research engineer at Instituto de Aeronáutica e Espaço and Institute of the Department of Aerospace Science and Technology of the Brazilian Air Force and an adjunct professor at ITA. He's a fellow of the American Institute of Aeronautics and Astronautics and a member of the National Academy of Engineering in Brazil. He is currently the president of the International Council of the Aeronautic Sciences, ICAS, the first Brazilian to occupy the direction of this association that brings together national institutions with an interest in the aeronautical sector from several countries. Azevedo has experience in the aerospace engineering with emphasis in aerodynamics, elasticity, and his research focuses and encompasses computational aerodynamics, computational aeroelasticity, and CFD. Today, he's going to talk about high lift flow simulations. Please, João, the floor is yours.
Thank you, Sandra. Thank you very much. And hi, everybody. It's really a great pleasure to be here with you guys today, okay, and be able to share a little bit of the work that we are doing in our group. Before I start, I really have to thank the conference organizers, Álvaro, Sandra, and Eduardo, for the invitation. I hope I do not let you guys down, okay? My talk today is on, as Sandra already mentioned, is on high lift flow simulations. And of course, I believe in teams, okay? And of course, what I'll be showing to you today, okay, is not my own work, is the work that we have done in our group. And I'm listing here the people that have contributed to this work. Just a brief outline of what I want to talk to you today. Okay, I will start and spend some time talking about motivation, okay, and really concentrate most of my time on some results that we have obtained. And as I said, the idea is to show to you some of the things that we are doing in our group, okay. I guess it's probably most of you are well aware, okay, that high lift flows are very important for aeronautical applications, okay. They are typically associated with takeoff and landing conditions. And there are several, key parameters or key performance parameters, okay, that depend on the high lift characteristics of the aircraft. And here I'm talking things like, maximum takeoff weight. Okay, maximum takeoff weight has to do with how many passengers you can carry on your plane, how much cargo you can carry on your plane. I'm talking about things such as, landing distance, takeoff distances, okay? People that live like in Rio are fully aware of that, okay? Landing at the Santos Dumont Airport is not a picnic, okay? I mean, it's not every airplane that can land there, okay? Because, of those key parameters which are associated, with the high lift characteristics of the aircraft. And of course, I'm thinking here, and you'll see that many of the results that I will show to you today have to do with, commercial airliners. But it does not only apply to commercial airliners. All sorts of aircraft have this sort of important characteristics which are associated to the high lift performance of the high lift behavior of the aircraft. Okay. Typically, the analyst is looking to determine, stall angle of attack, maximum lift coefficient, and those kind of quantities when you're talking about high lift conditions. Of course, as I already said, the configurations are operating at very high angles of attack. And what you do to be able to operate on those conditions is to extend the so-called high lifted devices. And actually, this increased the area of the wing, but then the wing that in those conditions looks more like a Christmas tree than anything else, and there are a lot of things that are there, and this, of course, can have an effect on the flow characteristics under those conditions. Therefore, I think what I'm trying to tell you is that, the configurations under these conditions are very complex configuration. And then you are flying very close to the stall angle of attack. So you're pretty close to flow separation. So the flow phenomena that might happen in those conditions are also very complex. And finally, of course, you're talking about aeronautical flows. Typically Reynolds number is very high and the flow is turbulent. However, at takeoff and landing, we're flying at low speed. So from our perspective, actually Reynolds number is not that high, which means then that the flow might go over some part of your wing as laminar, and then transition also becomes or may become an important phenomenon that you have to look at, okay? I will not have any simulation of this transition today to you, but it's just pointing out that transition might be an important thing. Instead of just, me babbling about those things, okay, this shows, a typical airfoil section with high lift devices extended. You have typically a slat, and on the slat cove, typically there is a vortex that is formed there, and this sort of merges with the upper surface of the slat boundary layer, and you have a wake that sort of comes out of that slat. This wake is going to flow over the main airfoil. Of course, the main airfoil also has a boundary layer that is developed on it. Maybe the wake would merge with the boundary layer, maybe not, as I'm showing here. There is also the main airfoil cove, okay, or the flap cove. This is where the flap is stored when the high lifted devices are stored, let's say, for cruise flight, okay. And also, so what I'm trying, I guess, to convey to you, okay, this can be very complex flows with merging wakes and things like that. And this is looking at a typical airfoil. If we look at the configuration that I'm showing here is called the trapezoidal wing, and or trap wing for short, okay? And here you're seeing on the left here, you're seeing the trapezoidal wing on the wind tunnel. I'm hoping you guys are being able to see my pointer here. Anyway, so this is looking at the upper surface of the wing, the lower surface of the wing, and you see the flat tracking device or flat brackets here, and also the slat brackets are in here. So this all complicates the configuration that you have to mesh and solve the flow over that, okay? And I'm showing here also a mesh, okay, for one airfoil section or one wing span-wise section for this configuration. And the particular section that I got here is the one that goes through the slat bracket. And this is, of course, a hybrid or a fully unstructured mesh. Okay? Typically, you grow you have, your surface mesh are triangles, and you grow prisms out of the surface, and then you fill all the rest of your domain with tetrahedra. And this here is another view of this configuration. In this case, there's an hexahedral mesh, and actually this mesh does not have the flat brackets or the slat brackets, but again, it is an hexahedral mesh. Okay? And this is, again, just to sort of motivate you to the fact that all of those things that are present in the flow might have an influence, okay? And here, what we are looking at are what we are looking at are isosurfaces, okay, of vorticity, which are colored by the velocity magnitude, okay? What you see, all of those calculations were for a Mach number of 0.2 and a Reynolds number of 4.3 million, okay? What you see on the left are results for a configuration without the brackets, either slat brackets or flat brackets, okay, at an angle of attack of 30 degrees. And what you can see, maybe there is some separation down here at the flap, okay, but aside from that, it's a mostly attached flow, well-behaved flow. And on the right here, what we see are results for a configuration with the brackets. And in this case, for an angle of attack of 16 degrees, already you see quite a lot of influence, okay, on the vorticity contours in this case, of the slat brackets, okay. And if you go to 24 degrees, a massive separation, okay, is already occurring. Whereas when you didn't have the brackets, even at 30 degrees, pretty much an attached flow. Of course, in this case, there's probably some effect, some numerical effects of grid refinement, things like that. But again, my point here is that, this brackets and all this kind of things that we need to have in these configurations, they can have an important effect on the kind of flow topology that we get, okay? And again, we in our group, okay, of course, we do simulations that are of interest of our institute, but our main job in some sense, okay, is to develop CFD capability that could be used by the institute or by anybody that will be interested. And we have an in-house developed code with which we have been working for quite some time. About 20 years, I would say, okay. And this code has been, continuously going through improvements. And the idea, to enhance the capabilities of the code, enhance the robustness or usability of this code. And in some sense, what I'll be showing to you today is part of this ongoing effort, okay, of developing this capability. And again, as I just mentioned, and since high lift configurations includes these complex and therefore interesting flow phenomena, they are ideal test cases for us to apply our developed solver in order to validate the solver or to help in the development of the solver. Another point, I guess, that is important to mention is that, that there have been some, people realize that those are important configurations. And therefore, there have been some workshops which have been organized by the American Institute of Aeronautics and Astronautics. And probably the most well-known of this workshop is the CFD drag prediction workshop. These are actually workshop series, in the sense that there have been at least 6 drag prediction workshops. And some time ago also started to have the high lift prediction workshop. We have had 3 of those high lift prediction workshops. And all the test cases that I'll be showing results to you today are from those series of workshops. And the good thing about those configurations is that, those are sort of open or free configurations. They do not have any, industrial secrets from Boeing or Airbus, Embraer, or anybody. So people can, do computations and share those results in a more open way, okay? So, essentially then, the work that led to the things that I'll be, showing to you today, they come from this continuous development of our in-house solver, such that it could become robust enough, to be used in the simulation of full aircraft flows. Of course, this work meant to evaluate the capability of this solver to handle, those realistic configurations, both with and without high-lifted devices. We do have quite a few turbulence models implemented in the code, but the three that are involved on the simulations that I'll be showing to you today, and probably the three that are most active in most recent years are these two, linear eddy viscosity models, the Spolarto Maros and the SST model, and this non-linear eddy viscosity model. And, you should have in mind, that at the end of the day, our final goal is to have a CFD solver that can be used in daily engineering work. A little bit, okay, I'll have only 2 slides about the theoretical formulation that goes into the solver, and I promise no equations at all, okay? So what we are assuming is that for the flows that we are interested, okay, the adequate model is the 3D compressible Reynolds-averaged Navier-Stokes equations. For all the cases that I'll be showing to you today, the flow is assumed to be fully turbulent. Like I already said, we've been using those 3 different models. And the equations are discretized into a self-centered finite volume method for general unstructured grids, okay? And again, there are no high order methods here. It's a standard second order finite volume method. We use the rho approximate Riemann solver for the numerical fluxes, okay? We obtain second order accuracy with a muscle extrapolation of primitive variables. Of course, some of the simulations that I'll be showing to you today are transonic, therefore you need a limiter. We do have other limiters implemented in the code, but the simulations that I will present today, we have used the Van Albada limiter. And there is a lot of work going on, especially right now, in terms of how you compute the viscous derivatives as cell faces. We do that in different ways, and I believe that it's most of the results that I'll be presenting to you today use this very simple sort of finite difference-like way. But I'll have more to say at the end, and I hope I have time at the end to talk about that, okay? And time integration use a first order backward order point implicit scheme, okay? This is sort of a busy slide, okay? I'm not going to go into all the details here, but essentially, probably most of you know, the Spolarto Maros model is a standard turbulence model used by the aerospace industry. It is a one equation model, and it is a linear eddy viscosity model. There are several versions of the Spolarto Maros model, okay? We'll be using here what I'll be calling standard Spolarto Maros model. It's based on the Spolarto Maros paper of 1994, okay? The other model is the shear stress transport model, or SST model. The SST is also a standard model in the aerospace industry. It's based on or was developed by Mentor. It is a 2 equation model. It's again a linear eddy viscosity model. And essentially the SST model is a blend of the K omega and K epsilon models. Okay? Essentially it has, switching functions or that sort of use a K omega model at the wall, and this sort of transitions, okay, to a K epsilon model away from it. And the third turbulence model that we'll be, showing at least some results to you today is a nonlinear eddy viscosity model. It's based on the work of Walling, Johansson, and later it was, improved by Helston. It's sort of an explicit algebraic Reynolds stress model, okay? The explicit algebraic Reynolds stress models typically are sort of constructed sort of on top of a linear eddy viscosity model. In this case, this model is sort of construct based on Mentor's model, okay? Actually, if you go look at Mentor's work, okay, there is something that is called the baseline model, or BSL model, and the SST model. The only difference between the baseline model and the SST model is on the definition of the eddy viscosity. Okay, all the equations are essentially the same. Okay, so essentially Helston's model, the Walling-Johansson model, is sort of built on top of Mentor's baseline model, and adding some additional terms that try to, or that attempt to bring some information of the anisotropy of turbulence, okay, into the model. And at the end, then it becomes a nonlinear eddy viscosity model, but you're still only solving two partial differential equations. Okay, so it's still a pretty inexpensive model compared to a Reynolds stress model, of course, right? So, okay, so let me move to some of our results. I have structured this. I'll talk first about two, I'm calling validation cases, okay? Those are two cases which are not high lift cases. Those are, cruise condition type of cases, but high speed, but transonic region. And later I'll talk about another two high lift configurations. So the first two configurations that I'm going to talk about is the Honor-IM 6 wing, okay, and the DLR F6 configuration. In terms of mesh generation, okay, for the Honor-IM 6 wing, we have used 3 levels of mesh refinement. Those are all hybrid meshes. Again, by hybrid mesh, I mean that we have a triangular surface mesh. We grow prisms out of the surface, and then, in order to be able to resolve the boundary layer, and after that, we use tetrahedral for the rest of the domain. Okay, and those meshes for the Honor-IM 6 wing were all generated in-house. The DLR F6 configuration. The Honor-IM 6 wing is a configuration that was part of the drag prediction, the first drag prediction workshop, and also the second drag prediction workshop. The DLR F6 configuration was a configuration that was introduced on the second drag prediction workshop. For the DLR F6 configuration, we have both a wing body configuration and a wing body pylon nacelle configuration. And we are also using 3 grids for those two cases. In this case, we have 3 hybrid grids and 3 hexahedral grids for each of those two configurations, okay? Again, the hybrid grids were generated in-house. The hexahedral grids we got from the DPW2 website, okay? This is a view of the surface mesh for the Honor-IM 6 wing, and the coarse grid, the baseline grid, or the median grid, and the fine grid. And this next slide sort of gives you a view. This is a cut, sort of mid-span, at the mid-span section, okay? So that you can see a little bit of the volume grid. Like I said, you have the triangular surface, you go prisms out of the surface, and then you put the tetrahedra in the rest. Okay, again, the coarse grid, the medium grid, and the fine grid. And this sort of tells you sort of the size of the grid. Just, again, for today's standards, they're pretty small grids, actually. Even the fine grid. Anyway, I don't expect you to read all this, and the main purpose of this slide is to tell you that we did look at convergence, okay? What you see in the plots here are the L infinity norm of the density residue, okay, for all of those calculations, and the flight conditions is Mach number 0.84, 3 degrees angle of attack, and Reynolds number of 11.7 million, okay? And the point, I guess, of the plots here, just to let you know that, well, we did achieve some sort of, of formal convergence, or at least some 3 or 4 orders of magnitude drop on the residue, okay? The flow on this condition over the Honor-IM 6 wing, and by the way, what we have here is the root of the wing, and up here is the tip of the wing. At this flight condition, Mach number 0.8, okay, you have a shock which has what some people call a lambda shape. A lambda shape in the sense that if you look at near the root of the wing, okay, you have 2 shocks. One shock near the leading edge, and then the flow reaccelerates, and then you have another shock for the downstream, okay? But these 2 shocks sort of get together and merge sometime around 80% or 85% of the span. In outboard sections, you only have one single shock, okay? And this is what we are trying to visualize here. So essentially here we have, a CP contour plot at the surface, and what you're looking at here are ISO surface of Mach number 1.4 and Mach number 1.12, just to demonstrate that you have these 2 pockets, let's say, of supersonic flow, and then 2, which are ended by a shock. Okay, I think I have here, I have some CP plots, okay? I'll try, I have a whole lot more, but I realized I would be able to do this in 45 minutes or less, I guess. Sandra wants me to do it less time than 45 minutes, so she'll get mad at me. So this is them, CP plots, okay? At a station at 45% of semi-span. And the color coding here is this. The open squares are the experimental data. Red dots are the results with the coarse mesh. The blue dots are the results with the medium mesh, and the green dots are the results with the fine mesh. These calculations were done with the explicit algebraic Reynolds trans model. Okay, although unfortunately the results with the other models are not that much not much different from this one. Okay, so essentially, okay, for this case, what you see, except maybe for the region of the second shock, the first shock is in here. Okay, this is in a span-wise station where you have two shocks. Okay, the first shock is in here, the second shock is in there. You see that the computational shock is slightly downstream of the experimental shock, and it does pay to have a grid refinement, and the resolution of the shock with the grid refinement is better for this case. Okay, I guess my next one shows a station, a similar situation. Okay, now at 65% of the semi-span. Okay, not much effect of the grid refinement, maybe a little bit on the section peak, the section peak here near the leading edge, okay? But again, most effects of the grid refinement are at the second shock position, okay? And finally, one other station which is way outside, way outboard, I'm sorry, at 9% of the semi-span. Now the shocks have merged already, so we have one single shock. And again, in this case, what we are seeing is that the experimental, the computation results are sort of calculating the shock slightly ahead of the position of the experimental data. And the impression that we get, I mean, is that apparently the second shock sort of moves upstream a little bit faster, okay, or in a smaller distance, I guess, than the experimental data for the calculations, okay? Yeah, I think this is what I want to talk about. I may talk a little bit more about this test case. Actually, some recent result. This was like, I don't know, 2 weeks ago or so, okay? We sort of realized a few things that may improve considerably the results, especially with this turbulence model in terms of position of the shock. All right, let me move to my second configuration. And the second configuration that I want to talk about then is this DLR F6 configuration. Like I said, we have a wing body configuration and a wing body pylon nacelle configuration. What I'm showing to you here are the surface meshes over the wing. You can also see a little bit of the fuselage here, okay? For the hybrid meshes, okay? And here is the coarse mesh, baseline mesh, and fine mesh, again, wing body and wing body pylon nacelle configuration. And this is sort of gives you some idea of the size of those meshes. Again, for today's standards, not very heavy meshes, not that large meshes anyway, okay? And here are those meshes we generated in-house, okay? And the hexahedral meshes, again, we're looking at the surface mesh, okay? Those we got from the DPW2 website. Again, as before, the coarse mesh, medium mesh, fine mesh, wing body configuration, and wing body pylon nacelle configuration here in the bottom. Again, some information on the size of those meshes, okay? And here is my attempt to put in a single slide, okay, some visualization of the volume meshes. And what we are looking at here is a cut through a wing section which has the nacelle and the pylon. Of course, I mean, for the configurations that are the wing body alone, it is the same, span-wise station as this one here. Okay, such that you can have a comparison of the meshes. Again, on the top, you have the hybrid meshes for wing body alone, for wing body pylon nacelle, and on the bottom, the hexahedral meshes for it is the same station. It's always the same station, okay? All right, here we are looking at the drag polar, okay? This is drag coefficient as a function of lift coefficient for the wing body configuration. The Mach number here is 0.75, 0 degrees angle of attack, and the Reynolds number is 3 million, okay? And the color code here is the following, right? In red, the full red circles, okay, are the wind tunnel data. So this thing here. The other two red curves is just wind tunnel data plus or minus 50 drag counts. Okay, there's no reason for 50 drag counts. It's my plot. I do whatever I want with it. Okay, so it's plus or minus 50 drag counts, just that we can define a band around the wind tunnel data. Now, with the blue curves are the results with the coarse meshes. I mean, with the square symbols, the coarse hybrid mesh, with the round symbols, the coarse hexahedral mesh. I'm sorry. Okay. Well, in green we have the results for the medium mesh, and in black the results for the fine mesh. And essentially, I guess the bottom line here, or the overall message is, except for those results on the coarse hybrid mesh, which are way outside of this band here that we created, okay, all the other results fall within plus or minus 50 drag counts of the experimental data. In general, going from the hybrid grid to the hexahedral grid, even though the hexahedral grid has less cells than the hybrid grid, okay, tends to improve the results. And of course, grid refinement tends to improve the results. As I said, those are the results for the wing body configuration. The results for the wing body pylon nacelle configuration are not much different from that in terms, in terms of what we can take out of them. Again, it's the same flight condition, it's the same color coding. And as I said, going from the hybrid grid to the hexahedral grid improves the results. Mesh refinement tends to improve the results. And again, essentially, all the results fall within this plus or minus 50 drag counts with regard to the experimental data, except the results on the coarse hybrid mesh, which probably is really excessively coarse for this test case. Okay. Here is some visualization of the flow. In this case, we are looking at pressure coefficient contours. Here, essentially, mostly looking at the upper surface of the wing for the wing body configuration, wing body pylon nacelle configuration, and here looking underneath the wing or the lower surface of the wing. Okay. And this again, this is a pressure coefficient contour superimposed to shear stress lines. Okay, shear stress lines is a computational way of seeing what experimentalists call as oil flow. Okay, this is sort of our equivalent of oil flow in the experimental world. And I guess the only point to notice here is that the separation on the trailing edge of the wing near the wing fuselage junction is somewhat larger when you have the pylon and nacelle in the configuration than for the clean wing case. Okay. And I guess now I'd like to, I already mentioned all of this here. There's nothing there. Just I'm saying there that essentially the results are pretty good at all within this plus or minus 50 drag counts, except for the hybrid coarse grid. Okay. And now I'd really like to move to the high lift configurations. Okay. As I said, I'll show to you results for two configurations. Okay, all of those configurations they were part of the third high lift prediction workshop. One of them is called the high lift CRM configuration. CRM stands for Common Research Model, and again, this is something that was developed precisely such that people anywhere in the world could share their results. The CRM was actually a configuration designed by people like in Boeing, Airbus, and people, in actual industry. It was designed such that it could be, like the name said, a common research model, okay, that could be used for people to share. So there's no proprietary information in some sense, and that you can share data. Okay, so one of the configurations, this so-called high lift CRM configuration. The other configuration is called the JAXA, the Japanese Aerospace Agency. Okay, JAXA standard model. Okay, those are all the cases that were studied in the workshop. The results I'll be showing to you today are only these ones in green here. So I'll be showing results for this configuration called 1A, high lift CRM configuration 1A. And essentially, those are grid refinement studies at 8 degrees angle of attack and at 16 degrees angle of attack. And for the JAXA standard model of the JSM configuration, okay, we are going to do a full polar study, okay, for the wing body configuration and for the wing body pylon nacelle configuration, okay. Okay, for the high lift CRM, okay, those are the conditions. There's a lot of data here which is not relevant for us in this case. Important is the flight Mach number is 0.2. Reynolds number of the simulation is 3.26 million. And again, like I said, we're going to look at angles of attack, 8 degrees and 16 degrees, and we're going to do mesh refinement studies. Okay? We did not generate these meshes. We got these meshes from the workshop people. Actually, they were generated with a code called UNCSA. And again, those are all unstructured grids. I mean, they're called unstructured mixed grids. They are what I was calling before hybrid grids, okay? Such that you have an idea what the CRM or the high lift CRM configuration looks like. It has a full span slat here in the leading edge, and it has a partial span flap. Actually, there is an inboard section of the flap and an outboard section of the flap, and there's no aileron here on the tip of the wing. Okay, so this is what the configuration looks like. Looking at some lift coefficients, and here, like I said, we are looking at grid refinement. So here, what we're looking here is the number of cells in the mesh to the power minus 2/3. So essentially, coarse grids are to the right, finer grids are to the left. Okay. Again, the broken line are the results with 8 degrees angle of attack. The solid line results with 16 degrees angle of attack. This plot is like misleading. Say, well, you guys seem to be grid converging. So I did another plot over here where I enlarged the scales here for the CL. And what you're seeing is that we are far from being grid convergent. Okay, there's still 0.03 variations in CL as we refine the grids. Okay, and I mean, I don't remember exactly the size of those grids, but my guess from the numbers down here, okay, is that this coarse grid here has around 90 million cells, and the finest grid here has about, my guess is close to 200 million cells. So just you have some idea. And again, if you look here, especially for the 16 degrees angle of attack, it's clear that we are not grid converted yet. Okay, this is the drag coefficient now, and again, showing everything in a single slide, but this is probably more interesting. Again, showing to you that for this 8-degree angle of attack from our coarsest grid to our finest grid, you still have about a 60 drag counts in difference. This is a lot of drag. 60 drag counts is a lot, okay? So, I mean, we're still really far from being grid convergent, okay? And this is some flow visualization for those cases, okay? Now we are looking at the results. Again, shear stress lines, okay? We look at results on the top of the wing, coarse, medium, and fine meshes. This is for the 8 degrees angle of attack. And for this case, you see the flow is essentially attached over the wing, but there is some separation as you refine the grid, you see more easily over the flaps, both the inboard and outboard flap. And this shows you a little bit better the separation between inboard and the outboard. When we go to the 6-degree angle of attack, again, you don't see much of it. You start to see some separation here. I mean, towards the tip of the wing, there's still some separation in the flap, and this separation sort of grows with grid refinement. So quite a lot of separation seen on the fine grid results. And again, just looking at the flap, what you see is that the inboard flap now does not have any separation, but you still have separation in the outboard flap. Okay, and I'm going to show to you, I know my time is getting short, but I mean, I think I can show to you some CPs so you can see the comparison. I'll show you 3 stations. The first one's at about 28% of the span, okay? So again, the color coding here is black is the results from the coarse grid, red is the medium grid, and blue is the fine grid. For that span-wise station at 27.7 or 28% of the span. And what you see here in the inset is like the pressure peak, okay, the suction peak here near the leading edge of the main element. Okay, so in this case, except for, you know, here downstream in the flap, there's not much, at least at this station, there's not much effect of grid refinement for 8 degrees angle of attack. If we go to 16 degrees angle of attack, you know, the flow is attached, if you remember my other slides. So essentially, you don't see much difference due to the grid refinement on the CPU results. If you look closely at the suction peak, you see a little bit effect of the grid refinement, but there's not a lot there. Okay, now we're going to a station which is, you know, somewhere on the outboard flap or the region where you have the outboard flap. Okay, Again, at 8 degrees, we do see some effect of grid refinement, okay, in the main element, a little bit too in this section peak here. And again, quite a bit of effect, even at 8 degrees angle of attack, quite a bit of effect of grid refinement in the flap, okay? I mean, throughout the flap, even the suction peak in the flap and downstream in the flap, okay? And now if you go to 16 degrees, not a whole lot of difference, a little bit on the suction peak, but a little bit more difference though in the flap for this case. And maybe the more interesting case is the one on more outboard sections. I mean, this is a station at almost 95% of the semi-span. Again, at 8 degrees, we saw there was not much difference. Maybe you're seeing a little bit here in the slat now, but not much difference in the overall, behavior of the flow with grid refinement. But then we go to 16 degrees angle of attack. We see that separation, this flat CP distribution here, essentially showing that all this region here is inside that separated flow region, okay? And okay, let's me go to my last configuration. Okay, I want to leave you at least some 3 minutes or some 5 minutes or so for questions. Okay, those are the JAXA standard model or JSM configuration. Again, we have two cases now: a case with wing body alone, okay, and the case with wing body pylon nacelle. Again, a lot of information here. What's really relevant for me is the flight Mach number in this case is 0.172. Reynolds number is close to 2 million, 1.93 million. And again, we're going to do a full sweep in angle of attack. Again, the meshes were not generated by us. We got the meshes actually, we only use one mesh in this case, one mesh for each configuration in this case, right? And the meshes we got from the workshop, they all generated with this ANSAT code, okay? This is all, some visualization of this configuration. The wing body configuration, the wing body pylon nacelle configuration on the wind tunnel. This is a visualization of the grid generated, essentially the surface grid and the symmetry plane grid for the wing body pylon nacelle configuration. This is here some visualization of the volume grid, okay? Again, it's the same thing. I mean, it's a triangular grid on the surface. We go prisms out of the surface and then use tetrahedra in the rest of the grid. Just due to size of the grid, the wing body configuration is about 107 million cells, wing body pylon nacelle configuration 120 million cells, okay? We're looking here at the lift curve, okay, in the left for the wing body configuration and on the right for the wing body pylon nacelle configuration. There are two sets of experimental results. I mean, the dark blue results here are the so-called corrected experimental results. And by corrected, what we mean is that every wind tunnel has wind tunnel corrections, okay? So the corrected wind tunnel results are essentially the attempt by the wind tunnel people to represent something that will happen in free flight, okay? Because our simulations do not include the wind tunnel walls. And this is just essentially the raw, let's say the raw wind tunnel data are the incorrected results. And the red dots are our computations, okay? Essentially what you see for the wing body configuration is that, well, in the linear part of the lift curve, we're not doing that bad, but we're tremendously underestimating CLmax, okay? And our wing is stalling much sooner than the experimental data, okay? And at the workshop, what we saw is that our results are not that different from a lot of other people, okay? And surprisingly enough, or interestingly enough, okay, when you go to wing body pylon nacelle configuration, actually still not getting CLmax that well, okay, but we are much closer. We are much closer to the stall angle of attack, and I'll have some slides to show to you. Well, I'm not talking about drag. I don't have any time. I'll go to these slides of full visualization that help explain those kind of results, and I'll spend some time that you understand. There are a bunch of figures now, all they are the same way. What you have here on the top left corner, okay, is the oil flow visualization from the wind tunnel. Those are experimental results. And on the other figures, what you see are our results, and then we are looking at shear stress lines, okay, which again, like I said before, try to emulate the oil flow phase, okay. So this is a view on the top of the wing. This is a view essentially trying to look at the horseshoe vortex that's created at the junction of the wing with the fuselage. And there is also this fairing here, the wing fuselage junction has some fairing, which also creates a horseshoe vortex. Okay, so those are the results for the wing body configuration. And again, this is for 5 degrees angle of attack, very attached flow, everything nice flow. Then you go to 10 degrees angle of attack, and the horseshoe vortex becomes strong, but still pretty nice flow, very attached flow, everything all right. Then you go to 14.5 degrees, still attached flow, no separation yet. Then we go to 18.5 degrees angle of attack. There's no separation on the experiment, but you start to see some separation towards the wingtip, okay? Then we go to 20.5, 20.6 degrees angle of attack. The separation increases. You start to see some separation at the wing root. And then finally, for the highest angle of attack, at which we have the stall in the experiment, then you see the separated flow in the experiment. It's a lot of separation here on the inboard sections and also separation on the outboard sections. Then the conclusion of that, we're not really being able to get the same results for the lift curve, precisely because we do separate at the outer or at the outboard sections of the wing, whereas the experiment is still attached there. We do get the separation inboard, but we do get some separation here, which are not present in the experiment. Okay, and now let me move to the wing body pylon nacelle case. Again, it's the same thing. Okay, so 4 degrees angle of attack, attached flow, everything nice, clear. Oh well, now we do have some wake that comes out of the nacelle, okay, which also going to affect the flow topology over the wing here. Okay, again, 4 degrees angle of attack, 10.5 degrees angle of attack, all very nice and attached. Okay, experiment, very good match between experiment or our computation in the experiment. 14.5 degrees, still attached flow. 18.5 degrees. Now we still do not see much separation, maybe a little bit, but not essentially no separation here and there. Then 20.5 degrees, start to see some separation here, start to see some separation inboard. And then 21.5 degrees, again, now we do see the separation inboard, essentially inboard separation, a little bit maybe towards the tip of the leg. So the bottom line from this is that we do not get the exact lift curve on the wing body alarm configuration, because we are getting some separation outboard of the wing, which is not present in the experiment. Okay, but a very good match, okay, for the wing body pylon nacelle configuration. And then, for me to close it down, okay, guys, you are really looking at a work in progress situation. Okay, of course, by no means we understand this as a complete work. Okay, we're still working on that, so please bear that in mind. Okay, right now we are looking at more robust ways, maybe, of computing, viscous derivatives as cell interfaces. We found that this has a very important effect on the results, okay? Looking at different turbulence models, as I mentioned before, the Spolart-Marlos model has several versions, something called the nonlinear, the negative Spolart-Marlos, several versions of the model, okay? Looking at different versions of that. Also looking at coupling transition models. Unfortunately, I will not have the time to talk about this, but if you guys ask questions, I'd love to talk about this. We're implementing transition models to couple them with the Reynolds-averaged Navier-Stokes. We're also looking at ways of doing wall model LES for those kind of flows, okay? And maybe wall model LES, we'll be able to do LES, but with wall modeling, okay, maybe be able to do those kind of flows, okay? This is what I have. I did a little bit longer than I expect. Maybe I have a couple minutes for questions. Thank you guys very much. Again, thank you for listening. And again, thank you, Álvaro, Sandra, and Eduardo for the invitation. Okay, thank you.
Thank you. Thank you, João, for your very nice talk, very nice talk. We have just 1 minute for your questions, and then we have 2 questions from Álvaro. The first one, 2 questions about new methods. Meshing is always a problem. How do you see the acceptance by the industry of immersed boundary methods? Second question.
Let me answer that, or I'll forget. Let me answer that, then you ask the other one, okay?
Okay.
Great question, Álvaro. Great question, okay? For those, for those configurations, I'll use this one here, okay? Let me bring back the CRM. Okay, for the CRM configuration, okay, people are doing simulations for the high lift CRM configuration. And of course, the CRM is also going to have flat brackets, flat brackets, slat brackets, and things like that. And one of the possibilities that people that are working towards, I mentioned that there were 3 high lift prediction workshops. The 4th high lift prediction workshop is at the end of the first week of January now, together with the IAA SciTech Forum. And people have been working on this for over a year now, doing preparations for this workshop. And one of the things that they found out, some of the simulations that they are doing now, if they were to discretize all the details of the brackets and the support structure that exists, especially for this lab, okay, even with unstructured grids, they were not able to do it. So some people are doing those simulations using, Cartesian grids and inverted boundary techniques. Okay, this is something that people are doing right now, and hopefully we'll see results of that in the first week of January. Thank you for the question. Great question.
Okay.
So, there was another question, okay?
Okay, let's go. What about surrogate models for parameter exploration? Example, different angles or of attack, reduced order models, deep learning. Is the industry going in this direction?
Okay, well, I'm pretty sure there will be people look into those things, okay? We have not been involved in any of that. Okay, what we are looking at right now, and I start mentioning very briefly, is maybe being able to do those simulations using large eddy simulations. Okay, I mean, people probably would prefer to do, hybrid formulation like DES, DDES, and things like that. We went straight to hybrid simulations. Okay, but then you need to have those, the so-called wall model. Yes, otherwise the grids. I mean, the grid requirements in order to resolve the wall would be tremendous, and probably you would not be able to do that. But I mean, so again, we are not looking at those things, okay? But I'm pretty sure that probably there's someone out there looking at those things, because those are also pretty good ideas.
Okay, thank you, João. I think we don't have much time, so I would like to thank you, João, very much for your excellent talk. I hope to see you soon in person, maybe in the next CILAMCE, And then I will give the screen back to Álvaro to finish this section. Thank you very much.
Thank you again, Sandra. Thank you, guys. Thank you very much.
Thanks, Sandra. Thanks, João, for your nice, excellent talk. Now we have to move on. There will be our mini symposium sections, then our live discussions. And by 6 o'clock, we're going to announce the prize, the Research Beginners Prize, and our closing ceremony. We do hope that we can meet at the end of this conference, which has been very, very, very good to me. Thank you so much, and see you later. João, excellent talks. Sandra, very, 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 you handled very nice this session. Thank you so much. See you in a moment, guys. Bye-bye.
Bye-bye, guys. Bye-bye.
Ciao. Thank you, Álvaro.